let's talk about one of my all-time favorite topics, robotics. But this Chalk Talk isn't about a cute dog robot that can turn circles or some kind of dancing cobot. I'm sure you've all seen those videos. No, this Chalk Talk is about the mobile robotic applications that have become the backbone of our society. In our factories, in our fields, and our telemetry and mesh sensor nodes. What do all of these kinds of robots, big or small, have in common? The need for a flexible vehicle management controller. And more importantly, that controller must be able to provide precise control, AI driven decision making, and seamless connectivity. Because these systems need real time control and high performance for complex control algorithms, security protection from external threats and tampering, a flexible architecture suitable for a wide range of applications, and a whole lot more. And where should we go for this kind of flexible vehicle management controller to keep your next mobile robot running right? Right here, my friends. Right here. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Iain Galloway from NXP and I explore the benefits of the MR-VMU-RT1176 Vehicle Management Flight Controller from NXP. We also investigate the multitude of elements included in this solution and how NXP robotics platforms can get your next mobile robot design up and running in no time. And before we get started, don't forget to click that link. There you can find even more information about this topic from NXP. Hi, Iain. Thank you so much for joining me.
Yeah, it's my pleasure.
Excellent. Okay, so I am super excited to talk to you about mobile robotics today, and specifically a new vehicle management platform from NXP. But first, before we dig into the details, what's going on with robotics today?
Yeah, it's quite fast-moving and quickly evolving field. I think most people, if you're paying any attention, you'll see all this excitement and hype about humanoid robotics coming down the pipe and how this stuff can all help us in terms of our societal needs and industrial applications and agriculture. So there's a lot of activity in sort of these new areas, but there's also a lot of progress in the existing areas where you're talking about small vehicles navigating, how home cleaning robots, lawnmowers, and those sorts of things as well. But in general, we're seeing a lot more complexity coming down the pipe and very sophisticated, fully autonomous type systems. And that's where we're trying to get to here with these types of real-time controllers.
Fantastic. Okay, so can we dig in a little deeper? What specific applications or use cases are we talking about here?
So for this particular real-time controller, this VMU RT1176, it's targeted at the kind of things like inspection services and delivery with drones. It could also be used as part of environmental sensing systems. Sometimes those are not what you might think of as a robot. They're integrated into a bigger system, but a lot of the sensing capabilities and autonomy are still reused. And then, of course, there's factory and warehouse, marine equipment, boats and submarines are doing underwater inspection of docks or inspecting for environmental purposes what the growth of zebra mussels are in a certain area. I guess because of its flexibility, we also find that this type of system doesn't just get used in drones, but it gets used in the subsystems of other larger systems because it's capable. It's very computationally capable. It's got a lot of real-time sensor processing. So in that case, you find yourself as part of a sub-module that does a bunch of GNSS inputs or telemetry or communication with other systems. It's a very versatile type of platform. So the part specifically we're talking about is called MR-VMU-RT1176, and it is designed as like the heart of the real-time aspect of a small vehicle like a drone or a autonomous lawnmower or something like that. It's designed to take in lots of different sensors and process them locally, and then it may spit that out to a larger system. It might process them and then publish the results to some other larger systems as well. It has layers of security on it because, it does data logging on board, for example, and you want to secure that. You want to make sure flight logs are encrypted. You want to maybe certify that a drone is who they say they are, those sorts of things. So there's security provisions built in. And then, of course, it's a very flexible modular architecture. So it's designed to plug in what you need, the number of motors you need, the number of sensors you need, the payloads, and that kind of thing. So it's really built as a module that can be aligned with other modules.
Fantastic. All right. So talk to me more about what's under the hood.
Yeah, so I think as you can see, the picture here shows the reference design as we provide it. So there's a cube in the middle. So this is based on IMX-RT1176, and that's a dual core crossover processor. So it's a first gigahertz flight controller in the drone world. And there's actually a second core that we're not even using yet. So there's a secondary Cortex M4 core running there for other purposes. So you could farm off like some sensor, sub-processing systems over there to the 400 megahertz M4 core. The main core is a gigahertz M7. The other notable feature here is there's a lot of memory available on this because the crossover processors allow for external encrypted quad spy. We have more memory available for the microcontroller than anyone else. So it really opens up what the capabilities and sort of removes the restrictions on what could be done while keeping the costs very low because these external memories are way cheaper than having on-die memory. Now, in order to get the high processing speed, what happens is there's 2 megabytes of onboard RAM, tightly coupled memory that operates more at the chip speed. And that's how you get the high speed, high performance out of it. So that stuff's all up in the cube area, the black cube. And on the carrier board, we enabled it and we wanted to demonstrate automotive 2-wire Ethernet. So it's single pair Ethernet. So it's 100 megabit, 100 base T1 Ethernet. And it does have TSN for time-sensitive networking support for some more advanced applications. There's 3 CAN buses, and they also use our latest CAN signal improvement CAN-PHY, that's SICK, S-I-C, which cleans up the CAN signals and for help in very noisy environments or poorly terminated CAN buses, those sorts of things. And then all the other connectors are standardized to the drone code standard. So there's a standard that this is fully compliant to, which is called PixHawk V6XRT. And that's a hardware standard, not necessarily software standard. So the same hardware can be used in a variety of applications, and it just becomes extremely flexible with a big ecosystem of other things that are ready to go and plug into it.
And also walk me through all of the elements that are included here and how they work together.
Yeah. So as I said, there's that black cube on the top, and that cube is called, internally, it's got a subname of FMUM for the module. That's where the processor is. There's some sensors as part of that module board. So there's a barometer, one set of inertial sensors, IMUs, and that's like these accelerometers and gyros and magnetometers that are listed on the slide here. And then a secure element from NXP, an SE051, which is one of the FIPS compliant external hardware secure elements. Some other simple stuff like the memory we talked about, quad spy memory, the large amount of flash. There's an FRAM meant for very high speed writing, but it's non-volatile. And that's to capture things like flight logs. If there was a failure of some kind, you can do a quick dump of key flight log information, kind of like the black box in an aircraft. And then above that, you can see there's another IMU. So that's sort of there's a set of onboard IMU components. And then there's a separate little board that has a secondary set of IMU components for redundancy there. So that's, again, a subset of those sensors that are listed on the right-hand side. The carrier board is quite flexible. Like the connector standard is part of the drone code standard. So once you get down to the carrier board, you can fan that out to your own set of peripherals. On our carrier board as a reference, we give another secure element, and there's some security reasons for that, why you might want them on both. You've got external ports for things like I2C and SPY, a bunch of UARTs for telemetry radios and things like that. You've got 3 CAN ports available. You've got this 2-wire automotive Ethernet that I mentioned about. And then we provide USB-C for connecting with your laptop or doing configuration work. And then typically drones have like RC pulse width modulator outputs that drive motors and things like that. And also PWM signals that can either be traditional PWMs for servos or motor drives, or they can do something called D-Shot, which is a more advanced communication method to motor controllers and stuff like that. It's very complete and pretty much turnkey design. Someone can go to market, next week with this design if they want to. They don't have to change anything and it's fully ready to go.
That's fantastic. Okay, so Iain, what does this look like in a drone application?
Yeah, so when you're hooking up in a drone, there's a lot going on here, but this is typically what happens. You have bottom left-hand corner, there's some battery system. Often these are LiPo battery packs that go through a small power module, and the power module provides both regulated power to the VMU, and there's current and voltage measurement built into that power module. So you get a feel for battery health. That same power module feeds the power through to things like motors and servos and other sensors and actuators that might need a bit more juice. The PWMs are often feeding directly to motor controllers or servos. So you can see those at the bottom. And then there's a lot of communication systems on typical drone applications. So we've got like a radio remote control radio that has one input. There's another type of radio called DSM radio that can come in. So we've got two different ports depending on what kind of radio system you might be using for a remote interface. Often there's other types of radios like telemetry radios that connect to one of the UARTs. Those are providing the real-time data while you're operating the vehicle, when it's flying or it's a robot running around. It'll send data back onto where it is, what its GPS coordinates are, what its battery health is and status and all that kind of stuff. So back and forth. Also, that gets used to send up like missions and waypoint missions and things like that to the drone. There at the top, I'll show you there's often one or more GPS units or GNSS units. Sometimes there's real-time RTK, so for highly precise GPSs that are used, and that might need a secondary communication channel on one of those UARTs. And then various other sensors for a drone, like a pitot tube or airspeed sensor, they would plug in through I2C, or a lot of things have moved to CAN-based interfaces. So we have like a battery management controller, this BMS772 that has a CAN interface that could come in and give you really precise, accurate battery information, or another board called UCAN S32K16 that would be used for building like a CAN connected GPS or CAN connected pitot tubes and things like that. And then finally, the T1 interface is there and it's available to go over to things like a network switch or go directly to one of our companion computers like the NavQ Plus. And then if you wanted to connect into that from a laptop or something, we have adapters like the T1 adapter as well. So that's a typical configuration of a drone. They can be much, much more complicated and they can also be much simpler, but that's a typical sort of medium scale design.
I like it. Okay, so Iain, this solution is part of a bigger ecosystem, right? So what's all included in this ecosystem?
Yeah, I mentioned some of them already. We have quite a few reference designs. And again, all of these are fully open source. We provide all of the design files and then they run open source software on top of that. So it's easy to copy and build your own versions of these, and many of our customers do. So here are some of them. The NavQ Plus was one of our first companion computers, and that's a Linux machine, runs ROS2, Ubuntu, proof of concept, has camera inputs, has CAN interfaces, has T1 automotive Ethernet, the two-wire Ethernet we were talking about. We have that network switch, the T1 ETH8. Then there's an adapter. If you had a laptop you want to plug into this, or you had another single board computer you want to plug into this, you can use the adapter. Note that the Ethernet switch does in fact have an RJ45 connector and this other little tiny IX industrial Ethernet down below next to the NXP logo there. And that's a gigabit Ethernet connection that can go over to the companion computer, for example. And then some of the peripheral type boards, only showing a few of them here, but we've got battery management systems designs that are fully open, CAN node reference boards. And it's basically, one of our CAN chips and a couple of CAN PHYs on a board with you do whatever you want on the UARTs and I2C and sensors. It's just meant to be low cost and easy to build a peripheral. And then a more complicated board called a CAN Hub K344 that's got one of our automotive S32K 344 parts, dual lockstep core. So now you start using this as things like safety coprocessor, safety management in a bigger vehicle application. So there's a lot of ecosystem parts that go around it.
It looks like it. Okay, so Iain, what would this look like in a system?
When you really start building out a bigger robotic system, you end up with something like this where the vehicle management unit's there and it's got its own set of sensors and communications and safety control. So it's really the real-time control heart of the vehicle. it's got reflexes. So, you might have a sensor that's there that's telling you you're going to hit a wall or something like that. And the real-time controller can refuse to move because the companion computer is usually the one that's asking it to go somewhere or asking it to move in a certain way or pattern. Companion computers are doing, obstacle avoidance, mission planning, vision, processing, all that kind of stuff. So here we're showing, there's often one or two CAN buses for redundancy. There's often a 100 base T1 network where you may go between the vehicle management unit and companion computer with T1. And then things like additional cameras and things can plug in through a switch, an Ethernet switch. Sometimes motor controls are either driven directly from the vehicle management unit or they go through the CAN bus, as shown here. Battery management can hang off the CAN buses as well. Then CAN nodes might be for sensors or servos or other inertial measurement units. There's a lot of other building block pieces with our secure element, basically authorizing and authenticating each and every one of those things.
Talk to me about the software side of things. What does that look like?
NXP wants to make sure you have the freedom to do whatever you want to do, right? There's some specific software that's enabled on this specific hardware that makes it a drone flight controller or a vehicle flight controller. But, it is still a IMX-RT, the crossover processors, RT1176 on a board as a microcontroller. So you can do whatever you want. And we have all of our typical traditional NXP software and tools, the MCU Expresso, Zephyr enablement, FreeRTOS enable, and then all the design tools, etc. Those are all still available. It's just for this processor. However, for a drone in particular, we have properly and completely enabled it upstream with the PX4 flight stack. And that's one of the world's most popular drone controllers. It's open source. Our boards are supported fully upstream. And that lets you do things like GPS waypoint missions, surveying, and then connecting up to other systems that are running ROS and ROS2. That uses all open source tool chains like GCC compilers and stuff like that. And then on top, an additional sort of development areas, we have some newer and less established, but has some very exciting features like Cognipilot software. And that's designed primarily to host model predictive control. And the control software comes from external development. So you can have proper controls theory people tuning and building these model predictive control theory for a drone, a multi-rotor, an Ackerman steering vehicle, a skid steer vehicle, whatever. That's control theory. It gets synthesized and tested and then simulated on a vehicle, and then it gets compiled and plunked into Cognipilot that runs on top of Zephyr on top of hardware like this. And the nice thing with Zephyr is it lets you move it around depending on whichever hardware you want to use, because you're right, the code is written for Zephyr. It's not necessarily written for a very specific piece of hardware, as long as the hardware has the interfaces that are needed. These sorts of things really get enabled with a bigger robotic system using ROS2, a robotic operating system, which runs on Linux, and then simulation tools like Zeno for high speed or low latency communication. It's a really full ecosystem.
It seems like it. Now, Iain, I heard that you guys also have some even cooler kits.
Well, one thing to have a board, and it's another thing to have a robot. One of my pet peeves is I walk down the hall with these and oh, you got great toys. Well, no, they're real robots. They're full robots. They just happen to be small. And, they're general purpose robotic framework is what we're showing here. So we've got both a drone kit, the MR-HGK-RT, that uses this VMU RT1176 as the flight controller. And then you can add things to it like the NavQ Plus or a future board based on, say, IMX95. And it provides absolutely everything you need except a battery for a drone. And it's all certified. It can ship worldwide, all that kind of stuff. So it's really a proper full robot drone development kit. We also have another development kit for a ground-based vehicle, B3RB or Buggy 3 Revision B. That's also a complete kit, but for a ground vehicle. It's very similar to the drone kit. So nice to get started with real working hardware and references to be up and running successfully very quickly.
Absolutely. Okay, so Iain, if my audience wants even more information, where should they go?
So for the board itself, we have our nxp.com web pages. So that's at MR-VMU-RT1176 on nxp.com. But there's quite a few other resources for this board because it's more than just the hardware, right? It's all the software ecosystem. So if you're building a drone and you're going to use PX4, All of that is documented on the PX4 website in the upstream, main, how to build drone, how to configure it and fly and work with telemetry, all that kind of stuff. That's all standard. And there's developer pages both for our flight controller and a third-party commercial company called Holybro that makes the same flight controller. And so a lot of documentation you can cover. I talked about the newer Cognipilot vehicle control system. So that has its own GitHub and web pages. You can find that on cognipilot.org. There's Zephyr enablement. So if you just want to do a plain vanilla Zephyr project, go to zephyr.com. This RT1176 board is listed there, and you can see how to get started with a hello world and blinking lights and other examples. And in addition, for the drone kit, we do have our Git books, NXP Git books. So it's nxp.gitbook.io. And that comes from our Hover Games program where we have competitions based on the drones and rovers. And it's really like a how-to guide, an engineering notebook, how to assemble it, how to debug common issues, like if you get the propellers on the wrong way and stuff like that. So it's hand-holding you through all those processes. There's a lot of different documentation out there, but also very complete and ready to go to make you successful in this area.
Fantastic. Well, Iain, I think that's all I have time for today. Thank you so much for joining me.
Thank you.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from NXP. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EEJournal.